Hi, I'm Erika Oishi from the University of Electrical Communications in Japan. Today, I'd like to talk about enhancement of motion sensation by pulling clothes. So when we ride vehicle, our bodies were presented with various sensations. However, when we experience audiovisual contents with self-motion, such as race games, we perceive only vision. As a result, the presence of contents is limited. So various entertainment facilities incorporate the stimulation of the vestibular and somatosensory systems by actually moving the user's body in accordance with the presented motion. However, such devices tend to be bulky and expensive, which makes them difficult for home use. One solution to this issue involves the use of somatosensory cues. For instance, Isla developed chairs with numerous vibrators that vibrate in accordance with visual contents. And Daniel used haptic devices to shake the body parts of the user sitting on a seat and presented the force to user's body. So in these studies, each device presented skin sensation or force sensation. So my question is there any way to present both skin sensation and force sensation with simple and cheap setup to be used to enhance the perception of self-motion? So in this study, we propose a method of eliciting self-motion by pulling the clothes of participants while they sat on chair. This method has two advantages. One is that this system could induce both skin sensation and force sensation. The skin sensation is generated by friction between skin and clothes. And the other is that this system could present to a wide area of the body by just pulling a part of clothes. So as a result, this system is simplified. Based on this method, we developed the clothes pulling system. The clips with string attached to the shoulder part of the user's clothes. And using motors to rear-in the string, this system pulls the clothes backward and presents a traction force. The motors are current controlled by the microcontroller, and maximum theoretical traction is 80 Newton. And the purpose of this study was to present the sense of motion. So we must identify which physical property can be presented with our device: position, velocity, or acceleration. In other words, when we pull the clothes, is it interpreted as position, or velocity, or acceleration? To answer this question, we conducted the first experiment. Participants were exposed to an optical flow stimulus that moved forward and backward in a sinusoidal manner. We also presented the traction force, which changed according to a sinusoidal wave. Participants adjusted the phase of the traction force by keyboard to best match the feeling between the visual motion and the traction force. Hereby, we identified the physical quantity that users felt or interpreted when the system presented as traction force. 5 trials were carried out for each participant. The initial phase of the traction force was random, and the steps of the phase change was pi/12. For example, if the phase difference between the sine wave of the visual stimuli and the sine wave of the traction force was close to 0, and then the traction force was interpreted as position. If the phase difference was close to half pi, then the force was interpreted as velocity. If it was close to pi, then it was presented as acceleration. Currently, the negative component of the wave cannot be presented owing to system limitations, so only the positive component was presented. As the Newton's law states that acceleration is proportional to force, we hypothesize that the traction force produced by our system will be interpreted as acceleration. This is a result of the experiment, and the horizontal axis shows each participant, and vertical axis shows the difference in sine wave between visual stimuli and traction. Most participants answered that the traction was approximately half pi, and this means that when the traction was proportional to the velocity, they felt the traction was matched with the visual stimuli. Also, we hypothesized that the traction was proportional to the acceleration, but most participants interpreted as velocity. One possible reason is that estimating velocity from visual stimuli is easier than acceleration. But anyway, the result was almost unanimous. So in our next experiment, we employed traction force as a method to present velocity. The purpose of the second experiment was to evaluate effect of our method in a real gaming environment. We presented the visual stimuli for 3 minutes, and once with and once without the proposed device. Infinite straight line was presented, and the visual stimuli were moved by pedaling. After each condition, the participants answered questions on a 7-point Likert scale. They were asked to rate their feelings of movement, speed, acceleration, immersion, and enjoyment for each condition. Based on the result of experiment 1, we presented a traction force in accordance with the velocity. We also gave the stimulator thickness questionnaire before and after each condition to measure the degree of motion sickness. This is the result of the second experiment. The horizontal axis shows questions, and the vertical axis shows the average scores. As for acceleration and enjoyment scores, there are significant differences between two conditions by a Wilcoxon-signed rank test. So we can conclude that the device was certainly effective. On the other hand, most participants commented that traction force was unnatural because it was not presented in accordance with acceleration. So this was actually not consistent with the result from experiment 1. As I mentioned, in our current setup, we can only present backward force, which might affect both experiments. We intend to clarify this in future work by presenting forces in both directions. And this is the score of SSQ test. The horizontal axis shows the items of SSQ, and the vertical axis shows the score. Here I show the difference of the score between before and after trials. Positive scores indicate an increase in motion sickness after the trial. Wilcoxon-signed rank test revealed no significant differences between the two conditions. However, most of the scores were decreased by our system. So there seems to be a tendency of decreasing motion sickness with our system. I'd like to summarize this presentation. To enhance the perception of self-motion in audiovisual content such as race games, we developed the closest pulling system and made 2 experiments. The first experiment shows that the traction was interpreted as velocity. And the second experiment shows that this system improves the enjoyment of content. But the sensation was somewhat unnatural because traction was not associated with acceleration. One possible reason is the imperfect setting of the first experiment. Apparent limitation of our current system is that this system can only pollute backward. So we plan to develop a device that can present traction force in both forward and backward directions. This is the end of my presentation. Thank you for your kind attention.
Any questions? Yes.
Thank you for interesting talk. Now your system only pulls the close by just 1 point, right? Yeah. Have you considered about using multiple points, for example, shoulders or some other parts of the body? Yeah.
Yeah. I want to pull various directions. However, to do this, many motors need for this system. So now I think about using 4 motors, and this device can pull forward, backward, and right and left directions.
Thank you.
Any more questions?